I'm going to talk about something I found when we moved to Bazel at the Snowflake, a small interesting case. And I'm not going to talk about Snowflake at all, really, but I have to show you this disclaimer. You can read it on the slides later. It's a bit long. But yeah, what we're going to talk about is this regression that we saw, right? We moved from Maven to Bazel for our Java build in the mono repo. That's probably our biggest piece of the code base. If you're interested, there is a story I published there in the official Snowflake blog on how we went over this. But the main thing to talk about today is that we saw that most of our integration tests got slower with the migration, right? All of them became about 10 seconds slower, like as a constant factor. And this was a problem for developers because we spent a lot of time trying to optimize them, and then Bazel seemed to make things worse. So the question was, what happened there? Sorry. And what could we do about that? Now, to get into why this happened, I mean, it was pretty obvious when we look at the logs of the tests that there was something wrong with initialization of the test program because it seemed like class loading was slower, but the question was why. So to get into that, we need to first look at how Maven and Bazel compile Java code, because there are some differences there that you need to be aware of. And you can see on the right side, it's basically how the Maven model worked for us, where we had a bunch of modules, and each module is just a directory with a POM file and many Java files, right? And the way Maven compiles this, it takes the Java files, produces class files for each module in a separate target directory, and then when you go to run the tests, the class path ends up pointing at these target directories, and that's it. Now, for the Bazel case, which you can see on the left side, it's a bit different. We lost kind of the concept of modules because we defined the build files at a more granular level. So we ended up with many, many different Java library targets that represent finer pieces of these modules. And then you end up with many cross-dependencies across the modules. And every Java library that we define in the build file produces one separate jar. So then at the end of the day, when you run the tests, you end up with a class path that's much, much bigger because you end up referencing all these individual jar files. So there was obviously a difference, but the question was, why is this slower with Bazel when we run the test? But yeah, to recap, to give you some numbers, right? We went from about 400 modules in the Maven world to a few thousand targets with Bazel, right? It was a 10x explosion of the number of units to compile. As I said, Maven compiles these into target directories, and Bazel uses jar files. And then one interesting difference is that Maven doesn't have a sandbox, and Bazel does. So which one of these was a problem? Obviously, the first question, or the easiest thing to try was, is it the Bazel sandbox, right? Can we prove if it's a sandbox or not? Because that would be an easy thing to fix. But I did some measurements that there was no real difference between running the test with the sandbox or without the sandbox. The next question was, well, are the compression of the jar files a problem? Because in case you don't know, jar files are really zip files, right? And you can inspect them with zip tools as normal, and they are compressed. So I tried to disable compression to see if that was the cause, and no difference either. So it really was, there were too many jars. And the way I kind of proved that was by, I unzipped them all, I put them together by hand, and ran the test, and the test was fast. So it was pretty obvious that the number of jars was the problem. So we had to do something about that. So the easier way to try to fix this was, well, we can take this Java single jar rule that already exists, and we tried to use it for the tests. Now, there were some problems with this, but it was OK to get to a proof of concept. But the upstream single jar tool will silently ignore duplicate classes and duplicate resource files, and it will not be aware of how to merge some of them that are important for us, especially Spring Boot factories. So I had to actually fix this. I have some patches that I would like to upstream at some point, but I haven't had the chance yet. But now the tool will error out when it finds some duplicates that it doesn't know about, and it will also try to merge resource files that are important for us using whatever semantics they need. So with this, I could apply the single jar rule to each individual test, and this worked, right? We got the savings that we needed, but the problem is now you end up with these red boxes represent the single jar for every test, and these single jars are different for every test, because every test ends up with a different transitive closure of dependencies. So we ended up having to produce essentially 1 extra gigabyte of data for every single test that we had. And as I showed you before, there are thousands of tests, so this was just not a viable approach for our remote execution system. And there is also the problem that, compiling the single jar takes time, but we're lucky that compiling the single jar doesn't eat all the savings that we get at runtime. So this is still worth doing. So the idea to fix this was, well, what if we try to combine only the biggest module that we have, which is the one at the bottom that says monolith, because that's a gigantic target that we have in the build graph with many thousands of Java files. So maybe we just try to combine that into one single jar and leave the modules alone. Which you can see, maybe, if this thing passes. Oh, there you go. So this is the idea. We take this single jar target, we apply it to the monolith module only. We come up with one thing called mono, flat, or whatever you want to call it, that contains all the dependencies as a single jar. And then we make all the tests depend on this thing. The problem is tests have a transitive closure of dependencies that contains both the monolith and certain dependencies from the modules themselves. So you end up with duplicate entries in the class path. And that was a problem because the tests would, at runtime, error out and say, well, I don't expect two classes with the same, two versions of the same class, so I'm going to fail. So we had to prune those out somehow. And the way to do that was, again, with another custom rule that takes the path to the target that you want to combine and the name of the test, basically. It scans the transitive closure of all the dependencies of the test and removes those that will be combined later in the single jar. And then it kind of makes the test depend only on one version of either. Pretty complicated. If you want more details, I can talk to you about them later. But it kind of works. And then we get to the point where we have just basically one of these big jars for every PR, basically, instead of one for every test. And we still get the savings in time, and we only have to do this operation one when we compile all the tests. Now, can we do better? And the answer usually is yes, of course. One thing we're trying to do is to actually simplify the build graph, right? So if we have fewer targets in the Bazel definition of our compilation, right, we'll have fewer jars. So that's the first thing we're trying to do. But the more interesting thing that I have never gotten into yet is, does Bazel really need all these jar files, right? And I think it doesn't. But probably for historical reasons, before Bazel had 3 artifacts, it might have needed them to combine, to be able to express the fact that some Java files produce more than one class file, and you don't know that up front, right? So a way to hide that is by packing them into one file that you can declare in the build graph, and then Bazel can leverage that. But I think that with the 3 artifacts, or maybe you're using bug 2 and you can use the dynamic actions that we saw yesterday, these are things you could probably avoid, and then get to a model that's more similar to the Maven world and avoid all this craziness they had to go through. So yeah, to conclude, just be aware that moving to Bazel usually makes your build faster, but there are corner cases where it may actually make things worse. I told you about Java and the ClassPath, but we found something similar with C++, right, where many intermediate shared libraries cause the debugger to be much slower to start up. And then for other languages, I haven't thought about it, but probably there are some other pitfalls to be aware of. The good thing is that everything is Starlark now, right? So you could probably just rewrite the rules as you want to implement whatever compilation model you need, and then sidestep any problems that you might find with the standard ones. But if you have any questions, you can send me an email. You can grab me out later in the hallway, or you can visit my website, subscribe to my blog, and that's all. Thank you.
Thank you.